Hey guys, welcome back to another lecture video for Chem 104. In this lecture video, we are going to discuss our next functional group, which is an ether. So for those who like to play video games or know somebody who likes to play video games, you might have already come across this word ether. Ether in the video game world just represents this elixir or solution that recovers the magical points for a specific video game character so that the character can cast all these different spells and perform all these different abilities. And so, unfortunately, that's not what we're going to be referring to in organic chemistry. And so, when you guys hear the word ether, please do not think about this elixir. So, an ether is a functional group that basically represents an oxygen that's covalently bonded to two other alkyl groups. Okay? And so the arrangement of these two alkyl groups bonded to this oxygen atom is very specific. They have to be on either side of the oxygen. And so the alkyl groups, the identity of the alkyl groups can either be the same or they can be different. So let's go ahead and look at how we can represent just generally what an ether looks like. And so an ether can be represented by substituting these alkyl groups with this letter R, which is known as an R group. And so these R groups represents any alkyl or carbon chain. And it doesn't really matter what they are. All we know is that it's carbon based. And so you can imagine that you have an alkyl group or a carbon chain that's all single bonded, or you can have an alkyl group that has mostly a single bond between carbons and hydrogens. And then you might have another functional group, or you guys might have like a double bond or a triple bond in one of those alkyl groups or carbon chains. And so you guys can think about R groups like a variable in math, x, right? So we typically treat x as this like unknown variable, and we have to go through these motions to find out what the identity is of that variable. And so the same idea can be applied to R groups. And so this is the general depiction of R groups, ROR. And so notice that there's two different types, ROR prime and ROR. And so I'm going to go ahead and just copy and drag some of this stuff here that I already wrote before. And so if you have an ether that's abbreviated with R and R prime, so this right here, this little apostrophe looking thing, that's known as a R prime. And so this R prime is going to represent a different alkyl group than the one that's on the left. Okay. And so I'm going to go ahead and drag this statement down real quick, or up. All right. So this alkyl chain is going to be different than the one that's on the left with respect to oxygen. Now, if you guys have an ether in which they're just both R's and there's no prime or double prime or what have you, then you're basically telling the reader that you have two alkyl chains that are the same. Okay? So notice that this is just R and R, so therefore if R is an ethyl, for instance, then the other R must be an ethyl. Where if you have R as an ethyl, R prime could be a propyl or a butyl or whatever else, whatever combination you guys can think of. And so just to demonstrate the point with actual structures, here we have this ethyl, right? So notice that this ethyl that's on the left of the oxygen is the same as this ethyl that's on the right of the oxygen. And so these R groups are the same. And so we would try to represent them as just R and R if we wanted to generalize this specific structure. Here we have the CH3, this methyl group, and here we have this ethyl group. They're not the same, and so therefore the R groups are different. And so we would probably use, let me erase this over here. So we would probably use ROR prime to generalize this organic structure. And so sometimes it's really a little bit tricky or difficult to identify an ether in an organic compound. However, if you expand it, if you write an expanded form of it, it's a little bit easier to recognize. And we'll look at how this looks like in a skeletal structure a little bit later on. And so if you were trying to identify the presence of an ether in your organic compound, you're looking for a very specific pattern, which is COC. And so if you have a carbon that's single bonded to an oxygen, and that same oxygen is single bonded to a carbon, then this is going to represent your ether. Okay. And so it doesn't really matter if everything to the right of that carbon is a different or the same alkyl chain as the one on the left. It doesn't really matter. So we can just say that this is R prime, this is R. What matters is that we're able to identify that there is an ether in our organic compound. Now, this is not the only way for us to depict this type of functional group, this idea of a COC. There's another way that we can create an organic compound in which there's a carbon single bonded to an oxygen that's single bonded to another carbon. And that's going to be an epoxide. And so an epoxide is nothing more than an ether that's in a three-membered ring. And so if you are looking at this expanded structure, here we have this carbon, another carbon, and all three of those are single bonded to each other. However, since the R groups, the carbons, are connected, it forms this three-membered ring. And so whenever you have a three-membered ring in which you have an oxygen as one of the vertices, if you will, in that structure, like if you guys imagine this to be a triangle, and one of the vertices of the triangle represents an oxygen, then what you have is an epoxide. And so epoxides are highly reactive. So if you have a three-membered ring, there's a lot of steric strain to maintain that ring-like structure. And so epoxides are typically reactive, and they can undergo specific reactions to produce different substances. And so if you took the full year of organic chemistry, then you would delve into that topic a little bit more. And so, long story short, we have two versions of an ether. We have a linear form, and if you have the COC in the linear form, kind of like this, then this is going to represent an ether. Now, if you have a COC that is kind of cyclized or forms a ring, then what you have is an epoxide, not an ether. All right. And so let's go ahead and discuss the geometry of ethers. And so remember that the oxygen, the heteroatom oxygen, must follow the octet rule. And so it must have 8 electrons, whether or not it's shared or if it's owned. So here we have 1, 2, 3, 4, 5, 6, 7, 8. Okay. And so since this oxygen has 2 lone pairs, that counts as 2 groups of electrons. Here we have another group of electron. Here we have another group of electron. The electron geometry is going to be tetrahedral. However, if we're talking about the molecular geometry, it's simply going to be bent. And if you are talking about the bond angle between the two, it's going to be less than 109.5 since we have this bent shape. And the idea is that these full electrons are going to push down on this angle, squeezing this angle a little bit more inwards. And that's what's forcing the angle to be less than 109.5. And so it does have a molecular geometry similar to water. And because it has a bent shape, when we're depicting this ether as a skeletal structure, we must make sure that we're bending our skeletal structure. So for example, if we have, I'm just going to go back up. So if we're trying to depict this substance as a skeletal structure, here we have 2 carbons. So 1, 2 is right there. Here we have 2 carbons. Here I have 1, 2 as well. Okay. So remember, each point represents a carbon in the skeletal structure. And so between them is an oxygen. And so since ethers have this 109.5 degree or less than 109.5 degrees, we need to make sure that we're bending our skeletal structure. Okay? And so here we have this ethyl group that's found on the left. Here we have another ethyl group that's found on the right. And right in the middle is this oxygen. Okay? And so the electron geometry and the molecular geometry is suggesting that we have to depict the skeletal structure of ethers in a very specific manner. Okay. All right, so let's go ahead and talk about its polarity, so that we can better understand its physical properties such as melting point, boiling point, and solubility. And so looking at this specific substance, and I'm going to actually translate it in terms of expanded structure because I want you guys to understand the connection. So notice that the oxygen is covalently bonded to carbon. And if you were to count the electronegativity difference, and we did this in the first half of this course, you would find out that the change in electronegativity suggests that the value of the change in electronegativity suggests that this is a polar covalent bond. And so what that means is that there's going to be a dipole moment pointing towards the most electronegative atom, which in this case is oxygen. And so we have 2 dipole moments. They're both pointing in the same direction. And so since they're pointing towards this side, if you will, there's going to be a net dipole. Okay. So what this is telling us is that this ether, just this simple ether, is going to be polar. Also, we can determine that this ether is polar because we have the presence of those lone pairs, and they're not canceling each other out. It's kind of centralized in one location. And so the thing about ethers compared to alcohols, so if I were to draw an alcohol, so remember an alcohol is simply this carbon chain, whatever it is, and there's going to be an oxygen that's single bonded to a hydrogen. So this bond is also a polar covalent bond, but it's actually more polar than this CO bond. Okay. And so this OH bond, I'm trying to find this white space, so this OH bond is more polar than a CO bond. Okay. And so the change in electronegativity is going to be much higher. And since this since this ether, lots of circles, let me simplify some stuff. So since this ether has no hydrogen, then that means that ethers cannot create hydrogen bonds. And so they can accept a hydrogen bond, but it cannot induce a hydrogen bond. And so if the molecule that the ether is interacting with, can create or induce that hydrogen bond, then yeah, it can accept the hydrogen bond because oxygen is polar, but itself cannot induce or create hydrogen bonds simply because there's no hydrogens on the oxygen of the ether. And so what that tells us is that ethers, so if you have a solution that's filled with only an ether and nothing else but an ether, then the intermolecular forces that solution of pure ether can explore are London dispersion forces and dipole-dipole, in which dipole-dipole is going to be the more dominant intermolecular force between two ethers. Okay? And so we're talking about an ether-to-ether action. Ether-to-ether action cannot form hydrogen bonds. Where if you guys have alcohols to alcohols, since both of those substances contains that OH group, then those two alcohols can form a hydrogen bond. And so what does that do with respect to alkanes and alcohols? Well, because ethers have a stronger intermolecular force than alkanes, so remember that dipole-dipoles, I'm just going to list it out here. So this ether, so we're talking about ether on ether action, right? And so this ether, or a group of ethers, can only have London dispersion forces and dipole-dipole. But dipole-dipole is the most dominant intermolecular force because dipole-dipoles are stronger than London dispersion forces. And so alkanes, they're just a whole bunch of carbons and hydrogens. And so alkanes can only access like London dispersion forces. And so with alkenes, the larger your molecules, the stronger those London dispersion forces are, because you have just so many of them because your molecule is big. But when you guys are comparing the same molecular weight between alkanes and ethers, since ethers have a stronger intermolecular force, since it can exhibit a stronger intermolecular force, it's going to have physical properties that are greater than alkanes. But since ethers do not have, so since ethers cannot form hydrogen bonds with other ethers, its physical properties is going to be less than that of alcohols. And so remember that alcohols can, we can find hydrogen bonds in alcohols. There's dipole-dipole in alcohols, and there's also London dispersion forces. And so because the dominant intermolecular force for an alcohol is a hydrogen bond, then it only makes sense for alcohols to have physical properties that's going to be greater than an ether. Okay. And so based on these three subjects that we're referring to, ethers, alkenes, and alcohols, we can kind of imagine that ethers are kind of like the middle ground. It's going to be found somewhere between alkanes and alcohols. And so once again, if we're trying to, if we have alkenes and alcohols and ethers that are of comparable size and shape, typically the ethers will have a higher melting point and boiling point than alkanes. And so if we're comparing ethers to that of alcohols, ethers will have a lower melting point and boiling point than alcohols. And so once again, it has to deal with their intermolecular forces. The stronger the intermolecular force, that means you need more energy to break them apart. If you need more energy to break them apart, then the boiling point is going to be much higher. The melting point is going to be much higher compared to intermolecular forces that are weaker. In other words, they're easy to pull apart. Once again, I'm going to bring up this analogy of magnets. The stronger the magnet, the more energy you need to separate them. And in terms of physical properties, that's going to translate into a higher melting point, higher boiling point, compared to magnets that you can easily separate. That doesn't require a lot of energy. And so typically, the melting point and boiling point for substances with very weak intermolecular force are expected to have a lower melting point and a lower boiling point. And so once again, we can, the same subject is going to be described in this slide. However, what I'm doing is I'm putting numbers to this just so that you can see. And so if you look at this alkane, this is a 3-carbon compound. And if you look at this alcohol, we have a 3-carbon compound. And more or less, this ether has like 3 points or 3 vertices. And so if you guys are looking at the boiling point, notice that the boiling point for alcohol is 97 degrees Celsius, whereas the boiling point of ether is negative 24 degrees Celsius. And so if you guys are looking at their structures, literally the only difference is this oxygen-hydrogen. And so since oxygen-hydrogen, when you have a group of alcohols, those group of alcohols can interact using hydrogen bonds. And so if you're trying to separate each and every single one of those alcohols, you need to invest a lot of energy to separate them. Therefore, its boiling point is going to be much, much higher compared to a molecule, such as an ether, who has an intermolecular force that's weaker than hydrogen bonds. In this case, it's dipole-dipole. And if you guys are looking at these alkanes, notice that alkane with respect to ethers, we're going to go from negative 24 and we're going to go even lower to negative 42. And so alkanes, they only have London dispersion forces. And those London dispersion forces are so weak, so easy to break, that you don't really need a high temperature for you to separate those molecules apart. Okay? And so this idea of intermolecular forces and how they translate into melting point and boiling point is something that we're going to explore continuously when we talk about one functional group to another. Okay. And so keep that in the back of your mind. Alkanes, they only exhibit London dispersion forces, and we're talking about pure substances here, right? We're not talking about like a mixture of alkanes to ethers. So alkane to alkane action, alcohol to alcohol interaction, ether to ether interaction. Okay. And so once again, ethers, their highest intermolecular force is dipole-dipole, and alcohols, their dominant or strongest intermolecular force is going to be hydrogen bond. Okay. And so in this case, for boiling point, we can summarize that alcohols are greater than ethers, which is greater than an alkane. So I apologize for what's the expression, beating a dead horse with a stick or something like that. In other words, I apologize for being a broken record, but I just really do want to convey as best as I can the trends for these physical properties and why we observe these trends for boiling point. The same can be said for melting point. I just didn't show it here. Now let's go ahead and talk about solubility of ethers. So whenever you're talking about solubility, now you have like this heterogeneous, this mixture, right? Where it's not, an ether interacting with an ether. It's now going to be an ether interacting with another substance. For example, water. Okay. And so in chemistry, water is our most common solvent. And so here, if you guys are looking at this ether, this dimethyl ether, and if you surround this dimethyl ether with a whole bunch of water molecules, the OH on that water molecule, as seen here, so this is going to be an oxygen and this is going to be a hydrogen. Okay. This oxygen hydrogen is going to serve as a hydrogen bond donor, and this oxygen that's on the ether is going to serve as a hydrogen bond acceptor. So H bond donor, H bond acceptor. And so these are just like fancy terminologies. The main point that I'm just trying to convey is that a hydrogen bond is formed. And so when a hydrogen bond is formed between a solvent and its solute, then perhaps the solute can be dissolved in the solvent, right? If those two molecules interact, then it's more likely that they're miscible with respect to each other. And so it turns out that only low molecular weight ethers, so if you have a ether that's 5 carbs, that's 5 carbons or less, are actually soluble in water. If you have a higher molecular weight ether, or ethers that have 6 or more carbons, it turns out that their non-polar character is going to dominate versus the the hydrogen bond that's observed between an ether and a water molecule. In other words, the longer the carbon chain, the more non-polar the organic compound becomes. And the more non-polar the organic compound becomes, the more insoluble it is in water. Okay? And so this is a chart that kind of demonstrates this idea of solubility up to a certain degree. And so here, if you have a 2-carbon ether, that molecule is so small that the non-polar character of these carbons are going to be dominated by the interaction of the oxygen to that of water via a hydrogen bond. And so therefore, if you put a 2-carbon ether in water, we would expect that we would get a homogeneous solution. In other words, it is soluble. And the same can be said about 3-carbon ethers, and so it's soluble in water. And so when you get to 4 carbons, it'll start gradually becoming slightly insoluble. So here we have a slightly soluble, slightly insoluble. So we're kind of getting into that range where if we increase the number of carbons, it becomes more insoluble. And so if we have 5 carbons, it's minimally soluble. I mean, it still does dissolve. And so between like 4 carbons and 5 carbons, we'll start seeing that slight separation of the solution. So you might see a slight layering of the solution in a test tube. So we might see a top layer and a bottom layer becoming a little bit more prominent. And so about 1 gram of it in 100 grams of water is soluble for a 5-carbon ether. 10 grams of the 4-carbon ether is dissolvable in 100 grams of water at a very specific temperature. So remember from one of the lectures in one of the other prior chapters, we discussed how temperature increases the solubility of substances. So same idea here. And so at very high temperatures, maybe this 4-carbon, 5-carbon compound, this 4-carbon, 5-carbon ether is going to be more insoluble compared to 25 degrees Celsius. And so for 6 carbons, it's insoluble, and so it's less than 1 gram. So 0.25 grams of the 6-carbon ether can be dissolved in 100 grams of water. So that means, the rest of it is not going to interact with water at all. And if you guys are looking at the structure for a 6-carbon compound, notice that here we have this longer carbon chain on either ends of that molecule. And so this non-polar character of the ether dominates over the small polar area of that ether. Okay. Compared to, for example, a 2-carbon. So here we have the polar part is really, really dominant compared to the non-polar areas. Okay? And that's why 2-carbon ethers are soluble in solution. Okay. All right. And so let's go ahead and talk about where these ethers can be found. And so I'm not too sure if any of you guys like to cook, especially with like anise. Maybe like you're using anise to, I don't know, make it like an adobo or something like that. But if you look at anisole, or methoxybenzene. And so anisole is an organic compound. It's typically colorless, and it has a smell that's reminiscent of like an anise seed. And so it's typically used in natural and artificial fragrances, and it can be used as a precursor to produce other compounds. But anisole or methoxybenzene, it's typically found in anise seeds. And so I don't know if you guys like to cook or anything like that, but that's what gives it that specific aroma. Same thing with black licorice, right? And so guaiacol, hopefully I'm pronouncing that correctly, is another naturally occurring organic compound. And the main point of guaiacol is the fact that it's a precursor to a whole bunch of other substances. And so, for example, if you have guaiacol, you can perform a specific chemical reaction that would, you know, produce anisole, methoxycyclohexane. We can produce benzene, cyclohexane. The list just continues. Here we can have a diol, right? So we have two alcohols that we can form from guaiacol, and the list just continues. And so guaiacol is biosynthesized by various organisms. However, the aromatic oil is derived from a specific wood. It's guaiacum wood. So this is the wood that I'm referring to. I can't pronounce these. And so this is anise. Star anise. Oops. So this is the guaiacum wood. And also traces of guaiacol can be extracted from celery seeds, tobacco leaves, orange leaves, lemon peels, and the list goes on and on and on. So those are, some sources, some natural sources for guaiacol. And if you guys are looking at both anise and guaiacol, I wonder if you guys can identify where the ether is. Okay, so I'll let you guys take a look at these two structures, the one on the top left, the other one on the bottom right. So where are the ethers in this substance? Okay. And so this is the ether. This is the ether. Okay. Now, in guaiacol, we have an OH, so this is the alcohol. And so, once again, these organic compounds, they're not primarily composed of only one functional group. It can be a whole bunch of functional groups can attach onto that specific organic structure, giving it different properties. And here, remember I mentioned earlier that epoxides are super reactive. And so here, if we have this central epoxide, if you treat it with nitrate, it can produce this compound. If you treat it with water, you get a diol, two alcohols. And just the list continues. You guys can go around in circles. You guys can look at the different products that's formed. And so these epoxides are super reactive, and enables a lot of organic chemists to be able to add on specific functional groups, creating new compounds. And these new compounds can probably undergo different types of reactions to produce more compounds. And so the domino effect just continues. And so in medicine, ethers are found in a lot of medicinal drugs. And so, for example, here I'm just going to focus on two. Citalopram. So citalopram is a drug that's typically used to treat depression, and it can also improve a person's energy level and feelings of well-being. And so citalopram, it acts more or less as a selective serotonin reuptake inhibitor. So it inhibits the reuptake of serotonin, allowing this neurotransmitter called serotonin to be more present in between the synapse of two neurons. And so, therefore, citalopram being an SSRI, it's going to increase the effective concentration of serotonin, uh, forcing it to induce, that signal. And serotonin is one of these neurotransmitters that's uh, associated to happy feelings, right? So that's one way of citalopram being able to quote unquote treat depression. And I'm not saying that it doesn't treat depression or anything like that, but uh, I'm not saying that citalopram is a cure. I don't even know why I said quote unquote. Anyways, that's off topic. Um, so this piece that I circled is going to be the ether in citalopram. Notice that citalopram also has a cyanide and a fluoro group, and here we have a tertiary amine. And so we have a whole bunch of functional groups to this organic compound. But the main idea is that citalopram contains an ether, right? And so hopefully you guys are getting used to recognizing ethers in organic compounds. And so if we are looking at this specific organic structure, there's a whole bunch of ethers just everywhere, right? Um, and so here we have an ether, here we have another ether, there's another ether over here, there's another ether over here. Now, as I'm circling each and every single one of these, ethers, notice that the left hand side of the ether and the right hand side of the ether, they can be completely the same or they can be completely different, right? So here's another ether right here. The list continues. So each and every single one of these substances, feel free to, excuse me, feel free to Google them to see what they do. But ethers are present uh, in medicinal drugs as well. Okay. All right. So the next lecture video that I'm going to discuss is talking about the nomenclature of ethers. So I'm just going to go ahead and cut it off right here. All right. I'll see you guys in the next lecture video, and we're going to talk about the name or how to name ethers.